Real-time examples: POWHC and batch transfer overflow. Proof of weak hands coin POWHC, originally devised as a joke of sorts, was a Ponzi scheme written by an internet collective. Unfortunately, it seems that the authors of the contract had not seen over/underflows before, and consequently, 866 Ether were liberated from its contract. Eric Benissard gives a good overview of how the underflow occurred, which is not too dissimilar to the Ethernaut challenge described earlier, in his blog post on the event. Another example comes from the implementation of a batch transfer function into a group of ERC token contracts. The implementation contained an overflow vulnerability. You can read about the details in PackShield's account. Unexpected Ether. Typically, when Ether is sent to a contract, it must execute either the fallback function or another function defined in the contract. There are two exceptions to this, where Ether can exist in a contract without having executed any code. Contracts that rely on code execution for all Ether sent to them can be vulnerable to attacks where Ether is forcibly sent. For further reading on this, see How to Secure Your Smart Contracts and Solidity Security Patterns, Forcing Ether to a Contract. The vulnerability. A common defensive programming technique that is useful in enforcing correct state transitions or validating operations is invariant checking. This technique involves defining a set of invariants, metrics or parameters that should not change, and checking that they remain unchanged after a single operation. This is typically good design, provided that the invariant being checked are in fact invariants. One example of an invariant is the total supply of a fixed issuance ERC20 token. As no function should modify this invariant, one could add a check to the transfer function that ensures the total supply remain unmodified, to guarantee the function is working as expected. In particular, there is one apparent invariant that it may be tempting to use, but that can in fact be manipulated by external users, regardless of the rules put in place in the smart contract. This is the current Ether stored in the contract. Often, when developers first learn Solidity, they have the misconception that a contract can only accept or obtain Ether via payable functions. This misconception can lead to contracts that have false assumptions about the Ether balance within them, which can lead to a range of vulnerabilities. The smoking gun for this vulnerability is the incorrect use of this.balance. There are two ways in which Ether can forcibly be sent to a contract without using a payable function or executing any code on the contract. 1. Self-destruct/suicide. Any contract is able to implement the self-destruct function, which removes all bytecode from the contract address and sends all Ether stored there to the parameter specified address. If this specified address is also a contract, no functions get called. Therefore, the self-destruct function can be used to forcibly send Ether to any contract, regardless of any code that may exist in the contract, even contracts with no payable functions. This means any attacker can create a contract with a self-destruct function, send Ether to it, call self-destruct of target, and force Ether to be sent to a target contract. Martin Swen has an excellent blog post describing some quirks of the self-destruct opcode, along with an account of how client nodes were checking incorrect invariants, which could have led to a rather catastrophic crash of the Ethereum network. 2. Present Ether. Another way to get Ether into a contract is to preload the contract address with Ether. Contract addresses are deterministic. In fact, the address is calculated from the CACHEC256 hash of the address creating the contract and the transaction nonce that creates the contract. Specifically, it is of the form address equals SHA-3 of RLP.encode of an array consisting of account address and transaction nonce. See Adrian Manning's discussion of keyless Ether for some fun use cases of this. This means anyone can calculate what a contract's address will be before it is created, and send Ether to that address. When the contract is created, it will have a non-zero Ether balance. Let's explore some pitfalls that can arise given this knowledge. Consider the overly simple contract in Ethergame.sol. This contract represents a simple game which would naturally involve race conditions, where players send 0.5 Ether to the contract in the hopes of being the player that reaches one of 3 milestones first. Milestones are denominated in Ether. The first to reach the milestone may claim a portion of the Ether when the game has ended. The game ends when the final milestone, 10 Ether, is reached. Users can then claim their rewards. The issues with the Ether game contract come from the poor use of this dot balance in both lines 14 and by association 16 and 32. A mischievous attacker could forcibly send a small amount of Ether, say 0.1 Ether, via the self-destruct function to prevent any future players from reaching a milestone. This dot balance will never be a multiple of 0.5 Ether thanks to this 0.1 Ether contribution, because all legitimate players can only send 0.5 Ether increments. This prevents all the if conditions on lines 18, 21, and 24 from being true. Even worse, a vengeful attacker who missed a milestone could forcibly send 10 Ethers, or an equivalent amount of Ether that pushes the contract's balance above the final milestone, which would lock all rewards in the contract forever. This is because the claim reward function will always revert due to the require on line 32. In other words, because this dot balance is greater than final milestone. Preventive techniques. This sort of vulnerability typically arises from the misuse of this dot balance. Contract logic, when possible, should avoid being dependent on exact values of the balance of the contract, because it can be artificially manipulated. If applying logic based on this dot balance, you have to cope with unexpected balances. If exact values of deposited Ether are required, a self-defined variable should be used that is incremented in payable functions to safely track the deposited Ether. This variable will not be influenced by the forced Ether sent via a self-destruct call. With this in mind, a correct version of the Ether game contract could look like this. Here, we have created a new variable, deposited way, which keeps track of the known Ether deposited, and it is this variable that we use for our tests. Note that we no longer have any reference to this dot balance. Further example. A few examples of exploitable contracts were given in the underhanded solidity coding contest, which also provides extended examples of a number of the pitfalls raised in this section. Delegates call. The call and delegates call opcodes are useful in allowing Ethereum developers to modularize their code. Standard external message calls to contracts are handled by the call opcode, whereby code is run in the context of the external contract or function. The delegate call opcode is almost identical, except that the code executed at the target address is run in the context of the calling contract, and message.sender and message.value remain unchanged. This feature enables the implementation of libraries, allowing developers to deploy reusable code once and call it from future contracts. Although the differences between these two opcodes are simple and intuitive, the use of delegates call can lead to unexpected code execution. For further reading, see loy.lu's Ethereum Stack Exchange question on this topic and the Solidity docs. The vulnerability. As a result of the context-preserving nature of delegates call, building vulnerability-free custom libraries is not as easy as one might think. The code in libraries themselves can be secure and vulnerability-free. However, when run in the context of another application, new vulnerabilities can arise. Let's see a fairly complex example of this using Fibonacci numbers. Consider the library in Fibonacci lib.sol, which can generate the Fibonacci sequence and sequences of similar form. The library provides a function that can generate the nth Fibonacci number in the sequence. It allows users to change the starting number of the sequence and calculate the nth Fibonacci-like numbers in this new sequence. Let us now consider a contract that utilizes this library shown in Fibonacci balance.sol. This contract allows a participant to withdraw Ether from the contract, with the amount of ether being equal to the Fibonacci number corresponding to the participant's withdrawal order. The first participant gets 1 ether, the second also gets 1, the third gets 2, the fourth gets 3, the fifth 5, and so on, until the balance of the contract is less than the Fibonacci number being withdrawn. There are a number of elements in this contract that may require some explanation. First, there is an interesting looking variable fib_sig. This holds the first 4 bytes of the catcheck 256 hash of the string set Fibonacci of uint 256. This is known as the function selector and is put into call data to specify which function of a smart contract will be called. It is used in the delegate call function on line 21 to specify that we wish to run the Fibonacci of uint 256 function. The second argument in delegate call is the parameter we are passing to the function. Secondly, we assume that the address for the Fibonacci lib library is correctly referenced in the constructor. Can you spot any errors in this contract? If one were to deploy this contract, fill it with ether, and call withdraw, one would likely revert. You may have noticed that the state variable start is used in both the library and the main calling contract. In the library contract, start is used to specify the beginning of the Fibonacci sequence and is set to 0, whereas it is set to 3 in the calling contract. You may also have noticed that the fallback function in the Fibonacci balance contract allows all calls to be passed to the library contract, which allows for the setStart function of the library contract to be called. Recalling that we preserve the state of the contract, it may seem that this function will allow you to change the state of the start variable in the local Fibonacci balance contract. If so, this would allow one to withdraw more ether, as the result calculated fib number is dependent on the start variable, as seen in the library contract. In actual fact, the setStart function does not and cannot modify the start variable in the Fibonacci balance contract. The underlying vulnerability in this contract is significantly worse than just modifying the start variable. Before discussing the actual issue, let's take a quick detour to understand how state variables actually get stored in contracts. State or storage variables, variables that persist over individual transactions, are placed into slots sequentially as they are introduced in the contract. There are some complexity here. Consult the Solidity docs for a more thorough understanding. As an example, let's look at the library contract. It has 2 state variables, start and calculated fib number. The first variable, start, is stored in the contract storage at slot 0, in other words, the first slot. The second variable, calculated fib number, is placed in the next available storage slot, slot 1. The function setStart takes an input and sets start to whatever the input was. This function therefore sets slot 0 to whatever input we provide in the setStart function. Similarly, the setFibonacci function sets calculated fib number to the result of Fibonacci of n. Again, this is simply setting storage slot 1 to the value of Fibonacci of n. Now let's look at the Fibonacci balance contract. Storage slot 0 now corresponds to the Fibonacci library address, and slot 1 corresponds to the calculated fib number. It is in this incorrect mapping that the vulnerability occurs. Delegate call preserves contract context. This means that code that is executed via delegate call will act on the state, i.e. storage, of the calling contract. Now notice that in withdraw on line 21, we execute Fibonacci library.delegate call of fib_sig withdrawal counter. This calls the setFibonacci function, which, as we discussed, modifies storage slot 1, which in our current context is calculated fib number. This is as expected. In other words, after execution, calculated fib number is modified. However, recall that the start variable in the Fibonacci lib contract is located in storage slot 0, which is the Fibonacci library address in the current contract. This means that the function Fibonacci will give an unexpected result. This is because it references start of slot of 0, which in the current calling context is the Fibonacci library address, which will often be quite large when interpreted as a uint. Thus, it is likely that the withdraw function will revert, as it will not contain uint of Fibonacci library amount of ether, which is what calculated fib number will return. Even worse, the Fibonacci balance contract allows users to call all of the Fibonacci library function via the fallback function at line 26. As we discussed earlier, this includes the setStart function. We discussed that this function allows anyone to modify or set storage slot of 0. In this case, storage slot of 0 is the Fibonacci library address. Therefore, an attacker could create a malicious contract, convert the address to a uint, and then call setStart of attack contract address as uint. This will change Fibonacci library to the address of the attack contract. Then, whenever a user calls withdraw or the fallback function, the malicious contract will run, which can steal the entire balance of the contract, because we have modified the actual address for Fibonacci library. An example of such an attack contract would contain this fallback function. Function with no parameter, public, open brace, storage slot 1 equals 0. Code comment. We set calculated fib number to 0, so if withdraw is called, we don't send out any ether. Attacker address .transfer of this .balance. Code comment. We take all the ether. Close brace. Notice that this attack contract modifies the calculated fib number by changing storage slot 1. In principle, an attacker could modify any other storage slots they choose to perform all kinds of attack on this contract. We encourage you to put these contracts into Remix and experiment with different attack contracts and state changes through these delegates call functions. It is also important to notice that when we say that delegates call is state preserving, we are not talking about the variable names of the contract, but rather the actual storage slots to which those names point. As you can see from this example, a simple mistake can lead to an attacker hijacking the entire contract and its ether.